We're working through the analysis of each refrigeration cycle component. We've just finished looking at analyzing the compressor part of the refrigeration cycle. And now let's move on to the condenser part. And so this video is going to look only at the condenser component, the refrigeration cycle. Remember, let's see. Well, we've got compressor, condenser. Leaving the condenser, we're going to go to the expansion valve to evaporator. That's really going to be where we're going to get our cooling effect for a refrigeration cycle, and then back to the compressor. So let's see, let's refresh our memory on where we're at. There's the overall look at our refrigeration cycle. Could be a heat pump cycle, of course, but let's say it's a refrigerator. We're going to focus on the condenser section. But of course, let's look at this overview. You see heat transfer is involved. Yes, the condenser is simply a heat exchanger. Steady state, steady flow, one inlet, one outlet. In the sketch, do we see the condenser lifting a weight? No. Do we see a shaft, a rotating shaft at a certain torque involved for the condenser? No, we don't. So it's going to be a pretty simple and almost like a review analysis of what we've already covered in this class. And what are we trying to do in the condenser? We're rejecting heat from the refrigerant, and it's going to the outside surroundings. Whether it's in your kitchen, outside surroundings of your kitchen, or outside surroundings of your outdoors if it's an air conditioning unit. Okay, so let's look at the TS diagram for the condenser process. So we're coming out of the compressor at state 2. So remember, this could either, if it's an ideal refrigeration cycle, it would be state 2I, or like your book would say 2S, because the compressor would be reversible and adiabatic. However, if it's a adiabatic compressor with irreversibilities, it would be state 2A, or as your book would say, state 2. So let's imagine that we've got the enthalpy. We've got state 2 pinned down in terms of pressure, which is usually given, and also somehow we have found H2. So we're going into the condenser as a superheated vapor, and we're cooling. We're cooling the refrigerant from very hot, and we're cooling at constant pressure down to a condenser. So we're condensing the superheated vapor all the way down to saturated liquid. So we're going to cool down until it's saturated vapor. We're going to continue cooling across the dome, saturated mixture, all the way to the point where coming out of the condenser, it's saturated liquid. Now that's associated with the ideal cycle. There are a few times you may be asked to do a homework problem where there is some slight subcooling, in other words, getting into the compressed liquid phase. But in general, in most cases, in most of my practical experience, I've considered the condenser outlet to be a saturated liquid. So this is very common to say that state 3 is the saturated liquid phase coming out of the condenser. So that's what our process looks like, a constant pressure process, P2 equals P3. And that's how come we're going down sort of this dogleg type line. We're cooling and condensing at constant pressure in the condenser. All right, well, what does your refrigerator condenser look like? If you pull your refrigerator out into the middle of the room, you can visually see your condenser of your refrigerator. It is this, so actually it's this one tube, the serpentine tube, okay, where the refrigerant is coming in really, really hot as superheated vapor. And darn it, I can't see on this sketch exactly where it's coming in, but one thing I would say is that since we know that saturated liquid is the outlet of the condenser, the outlet of this the serpentine tube is probably going to be somewhere low, right? Because gravity will pull the saturated liquid down, or it will settle down to its lowest point. So I'm going to say the outlet of this condenser is going to be down low somewhere, right? And the other thing is, you say, well, I see this tube that's going back and forth and back and forth. What are these vertical things? Well, they're essentially serving as fins, heat transfer fins that are sort of welded to this refrigerant tube, and that's enhancing the heat transfer. That's to get as much heat transfer as possible from the tubes to the surroundings. And so that these wires are would be considered heat transfer fins. Okay, and so let's see, what did I say? I have to refresh my memory on my textbook here. It says, observe how the condensing refrigerant flows downwards by gravity. That makes some good sense. Vertical rods serve as fins to enhance the heat transfer. Okay, so it's pretty easy to observe what the condenser looks like on the back of your fridge. What does the condenser look like if you have a whole house air conditioning unit? Well, the condenser is going to be located outside. So this is what you would physically see outside your house or apartment. Let's say the condenser. Let's go up to our schematic diagram. This is what's involved here. Q dot H is going out to TH, or in other words, the high temperature of the surroundings. So this red would represent TH, wouldn't it? So in summer operation, we've got our superheated vapor coming into these coils. Notice the same kind of idea that you've got coils that make sort of a basket. So when you're looking at this unit, the condenser coils are sort of in the outside, but they're also fitted with fins, heat transfer fins, typically made out of aluminum, to enhance the heat transfer. So what's going on here physically for this unit? Typically, we've got a fan. A fan is pulling air across the condenser coil. So surroundings air is being pulled across, like I'm trying to show in this sketch, and then that's heating the air up, heating the surroundings air. And so the hot air is being discharged upwards from this unit. And so that's where your condenser is, and that's the way we're transferring heat from the refrigerant into the surroundings, sort of with this fan and air flow. What else can you see here? It does turn out that inside this unit, which is essentially just a hollow unit, that's where the compressor is located for your whole house air conditioner as well. So the compressor, that loud compressor, is located outside. The refrigerant compressor is located outside within this unit. Basically, the thing you want to see here for the condenser analysis is these condenser coils on the outside of this sort of big rectangular box. How about the condenser on your automotive air conditioner? Well, it's going to look an awful lot like your radiator, except what's being condensed is the refrigerant. And so I would imagine, let's see, if I pick up, I'm going to say that the inlet to the automotive condenser would be up this high. That's where superheater vapor is going in. And I'm going to say that the outlet, the saturated liquid outlet, is going to be coming out from the bottom of this condenser. And so how are you transferring heat to the surroundings? You know good and well how it's working. As you're driving down the road, you've got surroundings air blowing across this serpentine condenser, basically one tube, one inlet and one outlet, so that it's a serpentine tube that's serving to condense the refrigerant. And so you can see in the cutaway, here's your condenser. It's going to be located in a very similar position as your jacket cooling water radiator. So what's your sketch going to look like? Well, this is kind of a recap of Chapter 4, I believe, where you've gotten good experience at analyzing heat exchangers, steady state, steady flow, open system, one inlet, one outlet. So I've clipped out what your condenser would look like. I'm showing state 2 going in, state 3 coming out with mass flow rate m dot. I'm showing that W dot out is 0. This condenser is not lifting a weight. There's no shaft protruding from the condenser. I'm showing that it's a constant pressure process, very little pressure drop. And Q dot in. What's Q dot in to the refrigerant? It's going to be a negative number because we're rejecting heat. And so in my world, I never sketch Q dot out. I don't do that, but I do label Q dot in is less than 0. Okay. And so that's the way I keep myself straight when I'm solving problems. So let's see, let's remind ourselves to get back to the book. Little qn is, well, that's Q dot divided by m dot, the rate of heat transfer divided by the mass flow rate, little qn. So we can write the first law. We've got no change in potential or kinetic energy for this open system. So we can write the first law, Qn minus W out, well, that's going to go away. We'll strike that out, equals H3 minus H2. Simple as that. So statement of the first law for the condenser, Qn equals H3 minus H2, and I'm going to expect Qn to be a negative number, right? So I would, how would I get H? Well, let's see. H2 I've got from my previous analysis. How would I get H3? Well, that's saturated liquid. And typically I know what P3 is. P3 equals P2. It's typically given. So I'm going to go to my refrigerant tables, go to the pressure table, and look up H sub F at P3. It's as simple as that to analyze the condenser. So the condenser rejects heat from the superheated vapor refrigerant. It transforms it into saturated liquid. Becomes easy to look up the enthalpy, which you're going to need, of course, in your analysis to determine the heat transfer or heat transfer rate if you have m dot of the refrigerant. And so it's as simple as that. And I think you think, well, that looked pretty easy. And it should look pretty easy because you've already covered those fundamentals in Chapter 4 when you covered steady state, steady flow, open systems, one inlet, one outlet. Let's see, what's next? Next is going to be the expansion valve. That's where we're going to transform high pressure saturated liquid into a cold refrigerant saturated mixture.